Oops. So reforming our carbonyl. This is fine. We have this species, and we have chloride around. And now, if we have pyridine also present in this reaction, so let's just have the pyridine pull the proton off. I'll draw this in a more conventional bond line structure, plus pyridinium chloride. That looked just a little bit better. Okay, so now as we're looking at this, notice what we've done is we started with an acyl chloride, and we end up with an ester. So we're converting between our carboxylic acid derivatives. I'll show this again in a second. I'll go back up. We started with an acyl chloride in the presence of water. Over here, we ended up with a carboxylic acid. So we can convert between our different carboxylic acid derivatives. We're going down the ladder in terms of the reactivity, starting with our acyl chloride, carboxylic acid. And notice the mechanism is the same, whether we're reacting with water on the top here, or this alcoholysis with methanol or whatever the alcohol might be. Okay, so let's look at a couple more reactions. And we won't go through every derivative in this kind of painstakingly slow route, but I thought this is a good one to start with. So good. Oops. All right, I'll go back up for a second. I'm seeing some questions here. So that's that. There's that reaction. Excellent. So Angela asked, what's the role of pyridine in the hydrolysis reaction again? So I'll show it here for the reaction with the alcohol, since so people can write this mechanism down. Pyridine is going to serve as a base overall, and it's going to act as a base, picking up a proton, and it's really serving as a base in two different roles. One is it's going to take the proton off, whether this be from HOH for water, the hydrolysis reaction, or whether it be the proton from the alcohol. So it's a good compound that acts as a base to pick up that proton. So that's where it works in terms of the mechanism. The other role that it plays as a base, I'll show both reactions here now, is it basically, I guess, is going to coordinate to the chloride here. So in both this reaction at the top to form the carboxylic acid, or I didn't write it here on the bottom with the alcohol, in the absence of pyridine, you generate HCl. So you generate, here's the proton, whether it be from water or methanol, and the chloride. So we're going to generate HCl. And a lot of times, in terms of the chemistry that you're doing, that could be bad in the reaction. But for every mole of this acyl chloride that reacts, you're going to generate a mole of hydrochloric acid. So if you have a compound that's not going to survive the formation of a strong acid, that's bad news if you wanted to do this reaction. So what you do is you add pyridine as a base so that it'll pick up the proton and coordinate it, and it forms this salt, this pyridinium chloride salt, which kind of, it sequesters the HCl so that your reaction doesn't become really acidic as it's progressing. So it acts as a base to both pull the proton off and also to prevent formation of hydrochloric acid in the reaction. So then excellent, thanks. To Lorianne's question, can we synthesize acyl chlorides from any of these compounds or just the carboxylic acid? In general, it's only going to be from the carboxylic acid. That's the only one that we're going to consider. So I'll scroll back up here. From yesterday, we saw that we have these three methods shown on the top here, and we focused on the reaction with thionyl chloride as a way to make acyl chloride on the right from the carboxylic acid. Now, there are other ways to make these acyl chlorides, but we'll only consider from the carboxylic acid. And then we're going to take the acyl chlorides or whatever and react them to form a lot of other compounds. But really, those compounds will not be able to go back up the ladder unless you have the carboxylic acid. So for this one here, I didn't draw equilibrium arrows for the reactions with the acyl chloride. In reality, these reactions are theoretically reversible, but practically they're not. In other words, it's going to go in this direction 99.999% of the time. I'll show later on some reactions with esters that are in equilibrium in the laboratory sense. And so drawing these as one direction arrows is a way of trying to emphasize that even though technically these reactions can be in equilibrium, because you could write a mechanism where it goes backwards, it's not going to go that way in a practical sense. Okay, excellent. So let's look at a couple more reactions with these acyl chlorides. And this one here is formation of an anhydride. So we're going to take on the top our acyl chloride. Looks like we're actually reacting with the carboxylic acid in the presence of pyridine. And we form this species here, which is an anhydride. So it looks like two carboxylic acids that have come together, but we've lost a water molecule. So that's where the name anhydride comes from. And we have our pyridinium chloride as well. This mechanism is pretty much the same. There's just one slight twist to it. So we have this, and if we're going to take and react this with our carboxylic acid, now here, even though we have this highly reactive acyl chloride, this is a pretty weak nucleophile. So unlike water or methanol, where the electrons are localized on that oxygen, now those electrons are delocalized through resonance and induction between the oxygen. So this is a really weak nucleophile. So if you're just to mix these two together, the reaction it will happen to some extent, but it'll be very slow. And it's more likely that any water that's snuck into your reaction is going to hydrolyze this. So instead what we can do is just add a little bit of pyridine. And this can act as a base. Not can, it does. And it's going to deprotonate this. So this one would be an equilibrium arrow. I'll just write this single arrow. We write the acyl chloride, and I'll keep it in the same way. And now we have this species, plus our pyridinium installed. So now we've generated a better nucleophile. So let's go ahead now and have this attack. Make that a little bigger. So here's our tetrahedral intermediate. What I'm going to do is flip this around so it looks more like our anhydride. Like this, plus our good leaving group with our chloride. So now all we have to do is we're going to kick out chloride, reforming our carbonyl group. We'll draw it down here. There's our anhydride plus chloride. And that's going to coordinate with the pyridinium species. So here we formed our anhydride. Okay, so very similar, just slight difference is that we have an even worse nucleophile in this particular case, but we can use a base like pyridine. Pyridine is used as a base. Others bases could be used, but it's not very nucleophilic, which is good. It's not going to attack this carbonyl group here. It's relatively easy to use. It's a liquid. It doesn't smell very good, but it's cheap, relatively cheap, relatively easy to work with. So crystal S is the carboxylic acid, a weaker nucleophile than water, and it is. And so if we were to compare the nucleophilicity of, I should make it blue if it's water. Nice. So in both cases here, if we're looking at the nucleophilicity here of water versus the carboxylic acid, I'll just assert here that the bottom one here is a weaker nucleophile, and then let's see if we can come up with an explanation for that. Here, notice neither compound has a negative formal charge on it. However, here the lone pairs of electrons are localized on that oxygen, and there's another pair there. Whereas here with the carboxylic acid, the lone pair of electrons are actually delocalized by resonance across the oxygens. Here we could write the resonance structures or resonance hybrid, and through induction between the two oxygens. So that means these lone pairs of electrons are actually much more delocalized compared to water. So that's going to decrease the nucleophilicity. So what we can do is increase the nucleophilicity by taking off the proton. So that now, even though over here in the right or middle part, we have resonance and induction, those effects stabilizing the conjugate base here, at least we have this negative formal charge that's being stabilized, which is going to make this carboxylate here, the deprotonated species, more nucleophilic than the carboxylic acid. So anything that something that you do to delocalize charge is going to make something less nucleophilic.